So we are at the course of astroparticle physics. We are going through overview of different subjects, right? Last lectures, we went first a little bit into the early universe. Then we found this problem of dark matter. We tried to look what are the evidences for dark matter. Then last time we were trying to look at the efforts that people do to directly detect dark matter particles in laboratory with devices like this. There is no success at the moment, so people are showing upper limits on the dark matter cross-section as a function of mass. And then we discussed that the capabilities of laboratory experiments are rather limited because we need to tune the experiment to some specific dark matter model. And there is a lot of dark matter models available, right? So we don't know what is the mass of dark matter particles, what are their interaction channels, and so on. Then I switched a little bit to, well, I changed my point of view, telling that maybe we should go back to astronomy and try to look for dark matter signal using whatever telescopes available, because we have a variety of telescopes working from radio band to some detectors that are detecting ultra high energy cosmic rays, so many orders of magnitude in energy. Maybe dark matter will show itself in some unaccounted anomalies in whatever data from lowest to highest energies. And then at the end of last lecture, I also switched to this image of Fermi telescope. The idea was that, well, maybe if dark matter signal appears, for example, here in gamma rays, we know that there is a lot of dark matter in the galactic center, so maybe the signal sits somewhere on the sky in the direction of the galactic center. But then we look at the map and we see that it might be difficult to find this signal because there is a lot of background. This background, something that is background for a physicist looking for dark matter, would be signal for an astronomer, right? So then I changed my point of view from, well, let's say, the first three lectures we were doing sort of astroparticle physics, right? So we were making accent on particle physics, and astronomy was a helper. So let's change our point of view from now on to particle astrophysics, right? So we would study these backgrounds of astronomical signals for their own sake, right? So it is also interesting. We already looked at different types of signals, right? Like these pulsars, pulsar wind nebula, supernova remnants, active galactic nuclei. So the next three lectures, I will go more or less in this direction, right? Looking at different types of objects. Occasionally, since this was a Fermi telescope map that in the energy band above 1 giga electron volt, this means that all the sources appearing on this map are operating one or the other type of particle accelerator, because GeV is higher than, well, to produce a GeV gamma ray, you need a charged particle with energy larger than GeV, and this is larger than the rest energy of proton, right? So let's try to see, maybe by the end of today's lecture, we will have some understanding of what kind of objects are the sources that are appearing on the map, where do they come from, and maybe we will try to already see how, on one example, how these objects operate particle accelerators. Maybe before going to the details of the objects, a sort of a refreshment of what I already mentioned on the at the first lecture at introduction. So we are talking about some instruments like this. This is the map of Fermi telescope that is in operations in space. It looks like the this, well, it's a black box in the sky. Actually, this is an example how particle physics serves astronomy, because the device was built by Stanford Linear Accelerator Center, SLAC, right? So these are particle physicists suddenly got interested in astronomy, and they built a detector that looks like a particle physics detector. It has two parts. One, the upper part, layer part here is called tracker, and the lower part here is called calorimeter. There is also some shield black panels here. These are also parts of the detectors. They are shielding the detector from particles that are not gamma rays. So the main detection method here is that the gamma ray entering the detector would be converted into a pair of electron and positron inside the detector in one of these layers. And then the electron and positron will go through the tracker, so it is possible to track their trajectory. And when we know the, we would measure momenta of electron and positron, and then by momentum and energy conservation, we would reconstruct the momentum of the photon, so the direction of arrival of the photon and the energy of the photon. This would make us a telescope, right? Because then what is this map? It's a 2D histogram of arrival directions of photons of these reconstructed events of gamma rays, right? From the trajectories of electron and positron. You even notice some granularity, so bluish dots are individual gamma rays, right? Sometimes there is a lot of them coming from the same direction. We know that there is a source over there. And then, well, I filter the events with to leaving only the events with energy, some energy, right? So I can do spectroscopy and imaging and timing, actually, because for every gamma ray, I record the arrival time. So if some source would suddenly decide to do something crazy at this moment of time, I would notice this, because if I do a time histogram of events coming from the direction of the source, I would know that it went into a flare, for example, yes? That's how the telescopes work in gamma rays. Then maybe another example, the Fermi data publicly available. I'm using them, Volodymyr is using them, so you will use them maybe in the exercises. Another example with which I'm working, but the data unfortunately not public, then it is called LASSO, so Large High Altitude Air Shower Observatory. It is also done by particle physicists. On occasion, it is Institute for High Energy Physics in Beijing, so it's a Chinese installation, who made a network of detectors like this. It's an area somewhere, Sichuan province in China. It's a circle of 1 kilometer square, instrumented inside with scintillator pads. So dots here are maybe, well, yeah, there is no resolution to see them, but there are on the ground scintillator pads, and there are small hills here. Well, this you see some granularity inside. These are water tanks buried underground, and then there is a small hill to make, of dirt to make it, protected from some particles from outside. So inside the water tank, there is photomultiplier. The idea here is that, let's say, in fact, in this telescope, the atmosphere of the Earth works as a particle detector. So the principle is the same. In Fermi telescope, it was gamma ray that was entering the tracker. Here, the gamma ray is entering the Earth's atmosphere. In Fermi, the gamma ray was producing a pair of electron and positron. Here, gamma ray produces electron and positron in the atmosphere. And then this electron and positron, they go further. They produce new gamma rays through Bremsstrahlung. The new gamma rays produce new electrons and positrons, and so on. Then there is a phenomenon of extensive air shower that multiplies the number of particles by dividing the energy of the primary particles democratically among all electrons and positrons. So at the end, when the shower reaches the ground, we have a lot of electrons and positrons with energies, maybe 100 mega electron volt. The sum of energies of these electrons, well, it depends, right? But it's a proxy for the energy of the primary gamma ray. And then on the ground, if the shower is vertical, we understand that all scintillator pads will fire at the same time, right? But if the shower is inclined, so the scintillator pads on one side of the detector of the array of scintillator pads will shower earlier than on the other side. So by measuring the time delay between firing of different detectors, we would know the arrival direction of the shower. Then by measuring the total signal elons in all scintillator pads, we would measure its a proxy for the total energy, which is the energy of the primary particle. Again, we have a telescope, right? So all we need is direction of arrival and energy of particle. The water tanks buried underground are done for a purpose like this. They serve more or less the same purpose as here. I forgot to mention this black pads around Fermi telescope. The part of the device is called anti-coincidence shield. So the idea is that, these are also scintillator pads, by the way. So the idea is that a charged particle, when it is going through this scintillator pad, it would produce a signal, right? It would scintillate, well, the pad would fire. But a gamma ray, it has larger mean free path, so with a good chance it will go unnoticed through this black scintillator pad and start interacting only inside the tracker. So in this way, the telescope is able to reject particles that are not gamma rays. So all protons, electrons, and so on from cosmic ray flux, they are firing the anti-coincidence shield, and the detector blocks itself. It tells that it's not the event that interests me, right? So here in LASSO, we cannot put an anti-coincidence shield at the top of the atmosphere, but what people do is that they use a property of the air shower like this. When we have a shower initiated by proton or atomic nucleus, the main interaction channel is not electron-positron pair production, but the process is called production of pions, particles made of two quarks. These pions, when they disintegrate, decay into with production of muons. And then the characteristic, difference between showers produced by gamma rays and showers produced by protons is that the proton-induced showers are muon-rich, gamma ray showers are muon-poor. And these tanks buried, water tanks buried underground, they detect muons because electrons are absorbed by dirt above the water tank. So then it's sort of anti-coincidence shield in the version of this air shower array. This LASSO installation, it also sees astronomical sources. You see a sample they made, let's say, a survey of, a galactic plane. They see sources at high energies. So here it is a map at 100 tera electron volts. So apparently there are sources in our galaxy that are able to produce 100 TeV gamma rays. The energies of charged particles responsible for these 100 TeV gamma rays are PeV, 10 to the 15 electron volt or so. So, we understand that somewhere in the Milky Way, there are particle accelerators that are more performant than Large Hadron Collider here in CERN, right? Because the particles in LHC are 10 TeV or so, yeah? So something to learn for astronomers. Of course, one of the topics of LASSO and Fermi is to search, for example, for dark matter, right? But for for people operating the detector, dark matter is a byproduct, right? Anyway, they would see, well, on occasion, LASSO would not see the galactic center because it is in the northern hemisphere, but an analog of LASSO in the southern hemisphere would see the galactic center if dark matter particles have energy 10 to the rest energy 10 to the 15 electron volt. We would detect them because they would one way or the other accumulate in the innermost part of the galaxy and start interacting, right? But otherwise, even if nature didn't play the game, if the particles of dark matter are not detectable for LASSO, still we learn something about the galaxy. Still another example, this is also a gamma ray telescope, looks completely different. It's not like Fermi, not like LASSO. It looks like a telescope, and the telescope is a bit, well, maybe oversized, especially the center one. This is an example of Hess telescope. It is made also by particle physicists from, well, the leading organization here is Max Planck Institute for Nuclear Physics in Heidelberg. So at the origin, the group is from particle physics. The telescope is in Namibia. Well, the largest telescope is sort of 27 meters in diameter or something like this. It's, I don't know how high is our building here. We have more or less, what, 3 meters per floor. 3 times 6, it's 18. So it's larger than this building, actually, the telescope. So yeah, how does it work? Again, it uses the atmosphere of the Earth as particle detector. It aims at detection of the same phenomenon of extensive air showers, but on occasion, it doesn't directly intercept air shower particles. It uses the effect of Cherenkov radiation. So particles, these electrons and positrons moving through the atmosphere, they move with the speed faster than the speed of light in the atmosphere. In this case, particles emit Cherenkov light. On occasion, it is a bluish light. So in principle, we can see this Cherenkov light by our eyes if they would be sensitive to the signal that exists only for 10 nanoseconds or so. We can do this, cannot do this because our eyes are integrating on a fraction of a second, maybe 0.1 second or so, yeah? Then here the camera is shooting movies of the volume of the atmosphere at the rate, maybe a gigahertz rate, right? So it's ultra fast camera. And what they see is that these air showers, when they start somewhere high in the atmosphere, go down in the atmosphere. So it's like shooting stars, maybe going in the opposite direction because the light is slower than particles. So these are Ron shooting stars, the shooting stars that are shooting from below to above, right? So then what do they measure? You see, this is like several telescopes. This is for stereoscopic vision. So they see the shower from different directions to have stereo vision like our own eyes, right? Why we do we have 2 eyes to do stereoscopy, yeah? So doing this, they are able to reconstruct the path of the shower of the shooting star in 3D. This gives the direction. And the total amount of Cherenkov light is a proxy for the energy. So they can measure, they can reconstruct the direction and the energy of the primary particle that initiated the shower. And then again, they use their own tricks to distinguish gamma ray showers from proton and atomic nuclei showers based on the, well, they do machine learning or so on the images, because the gamma ray showers are more nice, straight and structured because their gamma factor is larger. So the electrons of energies, I don't know, TeV energy, they have gamma factor 10 to the 6 or something, right? And protons and pions of the same energy have lower gamma factor. So the shower is fat because the particles go into larger angles. And gamma ray showers are nice and slim. So again, they have a telescope like this. Maybe still one more variation of our tools for high energy astronomy, or multi-messenger this time astronomy. This is another type of telescope that uses completely different type of particles. Still, just last year, they published a map of the Milky Way. They sort of see some reasonable stuff. This part is somewhere here. This is the galactic center. Region over here, right? I don't know exactly at the galactic center there is no excess, but overall the inner part of the Milky Way shines. This is this blue brightish region here. So they start see sourcing in a completely different way. On occasion, the device is detecting neutrinos. It's not gamma rays, but neutrinos are neutral particles. If there are sources somewhere else in the Milky Way galaxy producing neutrinos, neutrinos go along straight lines. And if we trace back their directions, we can make the same type of maps as with gamma rays, although with lower quality because it is difficult to detect neutrinos. So the statistics of neutrino signal is not so high. And the map is a bit blurry, right? So not very sharp here. How do they detect neutrinos? So this is an example of neutrino telescope. This is ice. This is exactly south pole of the Earth. So this is the ice layer. It is sort of 2-3 kilometers thick. They drilled holes in the ice and put a set of photomultiplier, large photomultipliers, maybe with balls like this, spheres like this. So a network of photomultipliers, it works as a tracker. What happens is that, let's say, a neutrino that crosses the Earth, it would interact somewhere inside the Earth and be converted into a muon, if it is a muon neutrino. And then muon would go out of the rock below the ice. And then they try to track the trajectory of the muon. Since it is a tracker, they know the direction of the muon, and muon is ultra-relativistic, and neutrino, by definition, ultra-relativistic. They also detect, by the way, I forgot to write, this is an energy somewhere above tera-electron volt, the sky map, right? So everything is relativistic. So by knowing the direction of muon, they know the direction of arrival of neutrino, and also the amount of light left by muon in the detector. This is again Cherenkov light because muon is superluminal of ice. So the amount of Cherenkov light produced by muon is a proxy for its energy. So like this, they sort of have a lower bound on the energy of muon because they don't know what happened to the muon before it entered the detector. But they have sort of an estimate of the neutrino energy and arrival direction, so it works like a telescope, okay? Now, with all these devices, we see more or less the same classes of sources. Let's try to understand now what are these sources. I don't know if you have comments for the first introductory part. It was a bit longer than I expected. Right, we started at 20 maybe, yeah. Some questions to the detection technique? No. So then the sources. So what I noticed that in the Milky Way, in Fermi map, I know what are the sources here. So all the bright spots like this, like this, like this, or like that, they are either objects that are called pulsar wind nebula. These are objects powered by neutron stars, or they are remnants of supernova explosions. So both pulsar wind nebula and supernova remnants have something to do with the death of massive stars. Yeah, this is supernova explosion is the last stage of evolution of a star. I think you all followed the introductory course to astronomy, right, on your second year. It's Frederick. So you have some memory of what is this. but I will refresh this memory now. So I want to understand what are these supernova explosions and pulsars and neutron stars. So for the rest of today, we will spend time on this topic. Let's get started then. If I want to understand the life cycle of massive stars, so the story here is that stars like our own sun, they will not explode they don't explode in supernova because their end of evolution is called white dwarf. So it's not that we are safe in our solar system. It's not pleasant to live next to a newborn white dwarf, but at least it will not explode. Stars with mass about 10 solar mass and higher, they end their life in explosions, and we can try to understand why is it like this. So the idea here is that, well, as long as the star is alive, it is in sort of equilibrium. The force of gravity balances the force produced by pressure. Okay. In the course of Frederick Corbin, you have perhaps seen the equation like this. This is called hydrostatic equilibrium equation. This is Newton's law applied for a small volume element of a star. What do we see here? On the right, we see the gravitational force, right, per unit volume, because instead of small mass, I put rho here. And on the left, I see the pressure, which is force per unit surface, and actually a pressure gradient, right? Because if something, well, if we imagine a volume element, it is pulled by gravity to one direction. To resist this gravity, we need a gradient of pressure that counteracts gravity. Otherwise, if pressure is equal on both sides of the volume element, the net force produced by pressure is zero, right? Just to be sure. So this is the second law of Newton. We can apply it well, here on Earth, it is valid. Inside stars, it is valid. What would interest me is the very interior of a massive star. So I will comment on this diagram on the right. What happens on the massive star? Any star starts its life by burning hydrogen into helium. This releases energy, and this released energy hits the medium. And well, if the star is a normal star like a sun, instead of P, I would put there the pressure of ideal gas or perfect gas, whatever. Gas parfait. So I would put just something that is N K Boltzmann T, the pressure and the temperature, the density and the temperature. And then, well, when the star is heated, the pressure grows. The star is heated to the degree needed to resist gravity, right? Now, when the star is heated, these nuclear reactions are possible because, well, somewhere inside the sun, for example, the temperature is millions of Kelvin. So protons, when they come together, they can do deuterium and then helium ultimately, right? A massive star, it has more gravity. So it would heat to larger temperature, and then further and further cycles of nuclear reactions become possible. The nuclear reactions in massive stars go up to the iron, which is the most bound element among chemical elements, right? So then as soon as iron is formed, nuclear reaction chain stops because beyond iron, all the nuclear reactions are endothermic. They consume energy rather than release energy. So energetically, it's not good to have those reactions. So gradually, if we take massive star, there is, well, of course, there is a segregation of elements by mass. So at the bottom of the massive star, there is sort of iron zinc. Yeah. And well, this nuclear waste in the form of iron forms a nucleus of the star. In this nucleus on the star, there are no nuclear reactions anymore. So the only thing this nucleus can do, it can cool down by releasing heat. And when it cools down, the pressure drops. And when the pressure drops, it gets more and more dense. Yeah. Ultimately, it reaches the density of sort of 10 to the 8 grams per centimeter cube. This is a huge density. This is unimaginable for us in laboratory. I don't know, do you have an intuition what is the density scales that are available for us? I don't know, my density is about what? Your density as well.
1,000 kilograms. Like the one of water.
1,000 kilograms per meter cubic, yeah? Well, in these units, EGS, it would be 1 gram per centimeter cube, yeah? The density of rock over there is about 3 gram per centimeter cube. In the mantle of the Earth, it's 3 gram. Inside the Earth, the density of the Earth's core is, I don't know, well, the average density of the Earth is about 5 gram per centimeter cube. So the densest things in the core of the Earth, they are this dense, yeah? Then in laboratory, I don't think that we are ever able to do something which is much more than 10 gram per centimeter cube, yeah? There, well, the machine is big, right? So the density reaches 10 to the 8 gram per centimeter cube. At this density, I don't know, the intuition should work like this. But actually, 1 gram per centimeter cube is a very natural density scale. If you take a size of the atom, what is it? Some 10 to the minus 8 centimeters, right? 10 to the minus 10 meters. So inside an atom, if you smear the atomic nucleus over this volume, it would be, well, 10 to the minus 8 centimeters cube, 10 to the minus 24. If I take 1 over this, it is the average density inside the atom, right? It's 10 to the 24 particles, so 1 gram per centimeter cube, 1 gram per centimeter cube, right? So inside the Earth, the atoms are squeezed, but not completely crashed, right? If I imagine 10 to the 8 gram per centimeter cube, so the space available for every atom, or is it atom or is it not, is, well, square root, this to the power 1/3, so it's -3. So it's every atom is 1,000 times smaller, right? Because the density is 10 to the 8, 10 to the 9 times smaller. So at this density, electrons start to resist. This is because, well, of uncertainty principle. Yeah, the electrons are fermions. We cannot put 2 electrons in the same state. So in the phase space. So in the phase space, every electron would occupy some minimal possible volume given by the uncertainty principle. Now, what I want to do, I want to calculate the pressure of produced by electrons that don't want to be squeezed. Yeah? The general formula for the pressure is its density times velocity times momentum. That's from the basic course of physics. Let's try to guess what is this pressure for a gas of electrons that follows this uncertainty principle. As I told before, I use the system of units where h bar is 1. So for me, it is 1 on the right. Then I can derive something from this uncertainty principle. For example, I can see that, well, I can, first of all, without uncertainty principle, I relate the space available for electron to the density, right? As I told, if I know the space available for every particle, I can convert it into the density estimate. Well, just by dimensional reasons, I can make something which is 1 over centimeter cube if I take 1 over delta x cube. Yeah. So the space available for a particle is the density to the power minus 1/3. This is the number density, right? If I re-express it through the mass density, it's like this. Yeah. Then now, well, of course, momentum is to the left or to the right, I don't, it's not interesting to me. By order of magnitude, the estimate is like this. This is the definition of momentum. And then I can relate the two. From the uncertainty principle, I know that delta P, which is this, MP, should be 1 over x, right? Should be 1 over x like this, which is then the density to the power 1/3. So it's an ingredient for momentum. I would use this expression that is through the density, right? Same for velocity. I would divide this by m. This would give me again velocity expressed through the density. And I already expressed delta. Well, this I don't need. So with this sort of transformations, I can express pressure through the density, right? What do I see here on the left? This is the density itself. I introduce here, by the way, Y is the number of electrons per nucleon. This is because the mass density is given by protons, right? These are protons, and neutrons are massive particles. Electrons have more or less the density equal to the number density equal to the density of protons. But for every proton, on average, we have 1 neutron, right? So if I'm converting number density into mass density, I should take this into account. So this Y is sort of 1/2 factor, yeah? So overall, with these transformations, I can express pressure through the density. If you follow this calculation, it will tell me that the pressure is proportional to the density to the power 5/3. This is the equation of state, right? So we know, well, we have seen equations of state here and there. So relation between density and pressure is called equation of state. On occasion, the state where electrons are occupying this, well, minimal possible volume in the phase space, it's called degenerate electron gas. So the equation of state of degenerate electron gas is P proportional to the rho to the power 5/3. That's some fact to know. And I will use this fact in this hydrostatic equilibrium equation now. Okay. I do like this. I expressed my pressure through the density. Here I also change the density to m over, no, I'm sorry, I'm not writing on the blackboard, but well, density is m over r cubed. I make an estimate for the density. I replace it like this. Density for the iron core is the mass divided by size to the power 3, right? I replace this by this estimate. And then on the right-hand side, what do? I also replace the density by mass over r cubed, so I can rewrite the right-hand side like this. And then I take the left-hand side, the right-hand side, I can simplify. Well, this is the order of magnitude equivalent of the hydrostatic equilibrium equation. If I simplify, I get something like this. I see that the size of the iron core scales as mass of the core to the power minus 1/3. Okay. This is in astronomy, it's a popular thing to do mass radius relations for stars. This is because, of course, for the iron core, we don't do measurements, but for stars, we typically can measure their mass. If they are in binary systems, we can measure their size. Sometimes we even resolve the image of the star. So this gives, this is an important source of information about the stars. Now, if I take this mass radius relation, I can derive some important fact about the iron core. Now let's come back to this evolutionary picture of the core. So somewhere in the middle of life of a massive star, iron starts to be produced and sinks to the bottom, forms a core. The core starts to grow because there is more and more of iron waste accumulating, right? When the core grows, its mass increases, and then according to this formula, the size shrinks. It's like these big belly containers, the waste bins, right? So it's self-compressing waste repository, right? So I add some garbage and it shrinks, it is squeezed in size, right? What happens is then the density grows, right? Because if the mass is larger, well, the size shrinks, the density grows. If I do the math, it grows as mass to the power 2, right? So now, next logical step, try to follow me. When the density grows, I come back to this uncertainty relation. If the density grows, where is my uncertainty relation? Yeah. If the density grows, the space available for particles shrinks, right? If delta X shrinks, delta P should grow. So the momentum of electrons grows, means that they becoming faster, right? Momentum is mass times velocity. Electrons are starting to move faster. Then the velocity of particles grows as mass to the power 2/3. And now let's come to the end of this process. The iron accumulates, the velocity can grow, as the iron accumulates, the velocity can grow only up to speed of light. It cannot become larger, right? So at some moment, the velocity gets to the speed of light. This happens, I can equate this to 1. My system of units, it's 1 velocity at the speed of light, right? So this happens, and then express the mass from this relation. This happens at the mass that is given by this combination. What I see here, I see proton mass, I see Newton constant. These are fundamental constant. This is factor 1/2 or something. This is this number of electrons per nucleon. So this is some combination of fundamental constants that has dimension of mass. Occasionally, this is 1.4 solar masses. Then the mass scale is known in astronomy. It's called Chandrasekhar mass. This is an important mass scale. At this moment, electrons become relativistic and something dramatic happens. Let's see what is dramatic about electrons getting relativistic. If I redo the same calculation as before, I only change one small thing. Before, my pressure was the number density times velocity times the momentum, right? But now my velocity is always speed of light. It does not depend on density anymore. And this changes everything. I do the same order of magnitude estimate for the pressure. It tells me that the equation of state has changed from rho to the power 5/3 to rho to the power 4/3. A small change, maybe nothing dramatic yet. But if I plug this back into the hydrostatic equilibrium equation, I see some bad thing. I see overall 1 over r to the power 5 on the left and 1 over r to the power 5 on the right. So r cancels, and I don't have any more mass-radius relation. I have just an expression for the mass, and it's always Chandrasekhar mass. So this means that equation of hydrostatic equilibrium of the core of the star does not have solutions for the masses larger than the Chandrasekhar mass. That's why it is important. What does it mean in practice? Imagine that I'm at the evolutionary stage when I reached this Chandrasekhar mass, and then there is one more nuclear reaction happens somewhere in the volume of the star. It produces just one more iron nucleus. And this just one more nucleus reaches the iron core and adds a tiny bit of mass to it. And that's it. So the core has to be larger than Chandrasekhar mass, but it cannot, right? This means that what is broken in this hydrostatic equilibrium? So now I see that the pressure gradient cannot resist gravity anymore. And since, well, there is not enough pressure, the core will start to collapse. Yeah. That's the end of life of massive star. And then everything goes very fast. So where is it? So I have an extra slide here. So when the core does not resist anymore, it collapses. If, well, in the first approximation, I would neglect the pressure. So if it is like this, the collapse goes on the time scale of free fall. The star was living, maybe these massive stars, they live maybe tens or 100 millions of years before. Now everything is gone on the time scale of free fall, 1 second or something. It's shorter than 1 second, the time scale. And well, then if there is no new source of pressure that can stop the collapse will go all the way to all matter would tend to fall to the very bottom of the gravitational potential well. So by default, our knowledge of physics nowadays suggests that it may be a black hole if nothing resists gravity. There is a small chance that maybe the collapse will stop at some level of density. This will be the density scale of atomic nucleus. Now try to do the same exercise as I suggested before. I suggested to estimate the average density inside an atom. It was about 1 gram per centimeter cube. Now, if we zoom an atomic nucleus, this is 10 to the minus 13 centimeters or something. 15, no, 13 centimeters. I'm always confused with meters because I try to convert between, yeah, minus 13. So the density, so if the space available for nucleons is 10 to the minus 13 centimeters, the density would be cube of this, so 10 to the 39 particles per centimeter cube. Then let's say a proton is 10 to the minus 4. Well, let me do the calculus. So if the space available for a particle, my delta x now is about 10 to the minus 13 centimeters. My density scale is 1 over delta x cube. It's sort of 10 to the 39 particles per centimeter cube. And then if I multiply this by proton mass, this will be the density in grams per centimeter cube. So this is proton mass. And proton mass is 10 to the minus 24 gram. So it will be something like 10 to the 15 gram per centimeter cube. So it turns out that this density scale can resist gravity because at this moment, nucleons inside this collapsing configuration become degenerate particles. They start to resist. The same way as electrons were resisting before, nucleons take over. And well, we can actually redo the same calculation as before for the electron gas. I would just remove this number of electrons per nucleons because we are talking about nucleons themselves. And then, well, in this way, I will get, again, equation of state that is pressure is proportional to the density to the power 5/3. I will get a stable situation up to the moment when nucleons become relativistic. Nothing changes, right? So the calculation is exactly the same. I just replace the word electron by the word nucleon. And then I will also find that, okay, I can have a stable situation of much smaller size supported by the pressure of nucleons up to some maximal mass at which nucleons become relativistic, right? The only change, if you remember, the expression for the Chandrasekhar mass was sort of like this, 2 fundamental constants combined. with the only difference that there was this Y factor here, the number of electrons per nucleon, right? It's gone now because the number of nucleons per nucleon is 1. So the analog of Chandrasekhar mass for this star made of nucleons is a bit larger than, by a factor of 4 larger than the Chandrasekhar mass that we found for electrons. So what is this configuration? I will explain what is this, and then we make a break, because I arrived at the point where I'm able to tell what is a neutron star. Remember this crab, the pulsar that I've shown at the beginning? It is powered by a neutron star. So what is it, neutron star? So it is exactly this configuration that is a collapsed stellar core that has reached the density of atomic nucleus. The density scale is 10 to the 15 gram per centimeter cube. That's really large. That's, well, there is no comparison with anything, as we discussed already. Already 10 to the 8 was large. 10 to the 15 is still more impressive. Just to, if we do the math, if we take the solar mass at this density, it would tell us that the whole star, the collapsed core, has a size about 10 kilometers. So the size of a larger Lausanne region. Yeah, maybe to Morsch, it's 7 kilometers or so when I run there. So it's this scale, right? But inside, let's say Lausanne, there will be the whole solar mass, right? It is very heavy Lausanne-like configuration. And then, as a matter of fact, this bizarre atomic nucleus would be very neutron-rich. Maybe I still take a couple of minutes to explain why is it neutron-rich. So, in everyday life, neutrons don't exist in free form, right? What do? They decay to proton. It's called beta decay, right? So maybe the reaction is like this. Well, it was written here, right? So this is the beta decay reaction. In fact, it's a reaction that can go in different combinations. For example, this reaction, if I throw a neutrino to the left-hand side, is also possible. Like proton combining with electron would give neutron and neutrino. So in everyday life, this reaction is common. That's why neutrons don't exist. But let's think about what happens in this collapsing iron core. Suppose that, well, the density is large, so neutrons can be created and destroyed, well, created through this reaction, destroyed through this reaction, right? But there is a peculiarity. If we take this reaction, so the electron is taken from degenerate electron gas. And then its energy is used to produce neutron and also neutrino that would escape, right? So in this reaction, some energy will escape from the star, yeah? Now, neutron wants to decay. And it has a bit excess energy, compressed energy compared to protons. So it tells I have some free energy. I can deposit this free energy into electron. Let's do this. I like to do this in everyday life, yeah? But, well, the medium around this neutron is saturated with electrons. So every cell in the phase space is occupied by electron. The only thing neutron can do, it can return this electron exactly into the cell from where this electron comes from, right? But this cell, it has very well-defined parameter. For example, it should be the cell at the energy level of this electron, right? But it cannot return this electron into this electron cell because some energy was taken by neutrino. It is gone, right? So the new electron that can be injected by neutron decay has no place to insert itself. That's why neutron decays get prohibited. And well, then conversion of protons into neutrons is allowed. but conversion of neutrons into protons is prohibited. That means that one important aspect of this process of gravitational collapse of iron core is the fact that the matter becomes neutron rich. It becomes so neutron rich that by the time when the size has shrunk to the size of 10 kilometers, most of the particles inside are neutrons. And the configuration is known as neutron star. Okay? Did you follow me? Good. So let's maybe make a break, and then we see what kind of properties does this neutron star have. Or maybe we also try to have a look. Yeah, well, let's try to make a break and then look more into neutron stars and also at some observational fact about this neutronization process. We have observed it once. Good. So now it's 9:15. Let's restart at 9:25. Make a 10-minute break.
So really?
There was like, yeah, basically like, I think 7 students in the lab. So like on the semester, they just come and they present the projects, and then you have to choose like which one prefers which project. And basically none of us have done any machine learning, and there were like 3 or 4 projects with machine learning. This is the problem. We're gonna like relearn on scratch.
Yeah.
So I'm learning.
Oh, that's nice. Can you like choose machine learning courses like now as well?
Yeah, no, it was only like last semester this machine learning course that we didn't take.
Yeah.
I'm planning on taking it next year. But yeah, I think it will maybe I guess.
It's used a lot.
Yeah, yeah. Maybe something new philosophy, or is it like even
Are you good at coding? Like,
Yeah.
where you are?
like,
That's-
I mean, for now, I'm not really presenting much learning part of it because I had to kind of give each learning. So that's what I'm doing up to like next week the vacation, and then I'll be yeah, trying to understand what I have to do. Yeah. I mean,
You're gonna be using like C++ or
But now on depends on the project. I mean, like React, for example, is using C and C from the root as well. So of the story. It's also really good. She never done any of both before.
yeah.
Just to learn everything.
It's kind of like learn coding. Like at the end of the course, I know this is fun. I like this, but then I don't do it for like half a year. Then I forgot everything. It's like syntax, you know. Yeah.
Maybe she's not working.
It's so annoying.
Yeah, it's kind of frustrating for me. It's yeah. I mean, it's nice when it works, but
Yeah.
for me, always it's a lot of time for it works.
Yeah.
Yeah.
Like once you're like once you can actually write the code and not just missing out parentheses or something.
There's just something that I wanted things in the place, like I'm trying to really do. So I just spend like half of my time coding
Yeah.
and half of my time just like on Stack Overflow, like waiting for me. What's the different colors?
Yeah, exactly.
I can explain like summarizing is this like really fun like
Yeah, exactly. It's so nice.
so much easier for this.
It's nice. Nice progression. It's kind of overkill, maybe.
So there's one person still somewhere. Let's restart. Come back. So the neutron stars. This yeah, just here on the right, it's a sketch of what can be inside this neutron star. Of course, in the first approximation that we understand is that the collapsing body should become neutronized. So in the first approximation, it's all made of neutrons. But of course, nobody has ever seen matter at densities 10 to the 15 gram per centimeter cube. So it's a nice object maybe for theoreticians and phenomenologists doing physics of strong interactions, right? Because inside, like inside the atomic nucleus, nucleons are bound by strong forces. So here it's the same thing on scale. And we know that strong forces are, well, maybe the right theory is quantum chromodynamics, that is nonlinear theory. So, well, we don't know if matter inside the neutron star, well, there are phenomenological models of strong interactions inside the nuclei, right? But, well, this diagram here shows the variety of possibilities of these phenomenological models. So somebody tells that maybe that neutrons disappear deep inside the star and form some quark matter, or maybe some other forms of matter. Yeah. So now, yeah. Also, this diagram is the continuation of the previous sketch, right? We cannot, of course, have a look inside the neutron star, but still we can always do what we tend to do with normal stars. We can measure basic characteristics of those neutron stars. For example, mass-radius relation. This sketch of calculation on the left is the same calculation as was for the iron core, right? It gave us some example of equation of state, the density proportional to the pressure proportional to the density to the power 1/3, which resulted in the mass-radius relation like size is mass to the power minus 1/3. Disappeared. I tried to transpose this size to the power equal to the mass to the power minus 1/3 into this mass-radius relation for the neutron stars. It would be a line like this, right? So mass is inversely proportional to the radius to the power 3, right? So it's a line like this. Now, people who do more precise modeling with account of strong interaction physics, they arrive at a range of predictions for the mass-radius relations. You see, they go like this. And there is a variety of models based on different phenomenological well, setups, right? Then, well, if we would be able to measure the mass and radius relation of neutron stars, we would sort of select, we would be able to tell which model is right. Ideally, well, we can have, in astronomy, we can do statistical studies, right? If we observe many of those neutron stars in different systems, one way or the other, we measure their masses and radii. So we would see the systems lining along some specific line, right? Then this would be an important input for physics of strong interactions. We will have one more type of data that constrains this physics, yeah? Maybe along the same line, how do we measure the mass and radius of neutron stars? In astronomy, we can measure the masses of objects if they are in binary systems. And just by studying Newtonian dynamics, Kepler laws, right? So we can weight the objects. This is an example. This is a sample of astronomical sources where we find neutron stars in binary systems. So the numbers here, they are usually the coordinates of the object on the sky. We don't give names for every next star that we see, right? There are so many of them that we just notice that the position of the star at the sky, right? So what do we see here? Where is our Chandrasekhar mass? 1.4 solar masses is here. It's reassuring. So there is a lot of systems where the mass of the object, which is neutron star, lines well along this line of 1 Chandrasekhar mass. To measure size of a star, it's also maybe intuitive. In the course of Frederick Courban, maybe you have seen a formula like this. If we think about luminosity of a star is typically a black body. So its luminosity per unit surface is given by this law, sigma T to the 4. Sigma is Stefan Boltzmann constant. If we multiply it by the surface of the star, 4 pi r square, it gives us the luminosity, right? This is valid for the sun. This is valid for no matter what star. This should be valid also for neutron stars. If their surface shines, imagine that we are able to measure the temperature of the surface, and we know the distance to the system so that we measure the flux of radiation from the neutron star. If we know the distance, we know the luminosity of the object, right? If we measure the luminosity and temperature, we can derive the size, right? That's the way how to measure sizes of stars. So this is sort of work in progress. So then, well, studies of neutron stars are aiming at testing this equation of state of nuclear matter, some branch of this astrophysics. Now, maybe if I come back to this neutronization effect, remember, right? So protons colliding with electrons, they can produce neutrons with emission of neutrinos. But then neutrons don't decay because, well, they cannot insert electron back into the degenerate Fermi gas. Now, one fact about these neutrinos is that we observed this process of neutronization once. Maybe I give some additional detail and then I show the observational data. So these neutrinos, I told that they escape from the neutron star, but it's not a one-step process. This is because the medium inside the neutron star is so dense that the mean free path of neutrinos, this is this combination, I don't know if you remember, we had a calculation more or less like this in the early universe. The neutrinos were coupled to the rest of matter of the universe or decoupled depending on what is the relation between their mean free path and the size of the universe, or Hubble radius, remember? Or what was the time before the next interaction compared to the age of the universe? That was the calculation. We can redo this same calculation. That's why I put, by the way, the same picture as you have seen in the cosmology lecture. We redo the same calculation for neutrinos that are trying to escape from the neutron star to see that it's not easy for them. In occasion here, what we would tell that neutrinos escape without problem if their mean free path is larger than the size of the star. Yeah. If it is shorter, what would they do? They would scatter inside the star, do a random walk. Yeah. Maybe ultimately they escape, but it would take them time to wander through the interior of the star to find their way out. Yeah. That's, by the way, what happens to photons in the sun. Initially, photons are generated in the core of the sun in nuclear reactions, but then they scatter off particles of inside the sun, it takes photons around 1,000 years to go from the bottom of the sun to the surface, to the photosphere. This is the layer at the surface of the sun. Within one mean free pass of photon from this layer, they escape, right? But it takes about 1,000 years to diffuse out to this layer. Curiously enough, well, in the sun, by the way, there are neutrinos produced, but neutrinos escape without problem from the interior of the sun. We detect those solar neutrinos with detectors on the Earth. So it's a story like this. But in the neutron star, it is neutrino that gets trapped because the density is so high. How can we see this? If I take the mean free pass of neutrino, this is as usual 1 over the cross section times the density. On occasion, this is the density that is 10 to the 39 particles per centimeter cube. Then I would get, well, I have an estimate for the cross section here. Anyway, if I do this comparison, I find that actually the mean free pass is shorter than the size of the star. This means that neutrinos do random walk and escape on the time scale that for the random walk, it is the formula for the time scale. We know it the other way around, right? We know that the distance of to which particle diffuses is growing as square root of time, right? It's the reverse of this formula. Now, it takes to neutrinos about 10 seconds to escape from the interior of the neutron star, yeah? Then occasionally we have observed once this event of neutrinos escaping, neutrinos from neutronization process escaping from interior of the star. This was a supernova explosion, not in our galaxy, but in the satellite of the Milky Way. It's called Large Magellanic Cloud. The supernova has exploded in 1987. It is called supernova 1987A. It was the first supernova exploding that year. It's not that every year that we have fireworks of supernova. We have them more or less several times per century in our galaxy. Well, since already 40 years, there was none. Maybe there will be one soon. We don't know. But, well, this is the event. So fortunately, already 40 years ago, there were neutrino detectors operational, and they managed to detect the pulse of neutrinos. Maybe I show the neutrino detector first. So the neutrino detectors that detected the pulse were like this. It's huge volumes of, well, this is one neutrino detector that is operational now called Super Kamiokande. It's a huge volume of water instrumented with photomultipliers. So these things on the side are photomultiplier tubes. So again, the effect is the same as, by the way, in ice cube. A neutrino arriving from the source would go, it can cross the whole Earth, but somewhere it would interact with something and be converted into muon. And then this muon would go through the volume with a speed faster than the speed of light, produce Cherenkov light. So then this Cherenkov light would illuminate some pattern of photomultipliers on the wall, right? And then when we, well, we would see a circle on the wall like this because Cherenkov light is directed, yeah? If we know the position of the circle, we look at the center of the circle, we backtrace it, so we know the arrival direction of neutrino. That's how people understood that the neutrino came from this source in Large Magellanic Cloud. This is the look of the supernova remnant today. Yeah, it's an image taken by Hubble Space Telescope not long ago. So the parent star was somewhere here. We actually know what was the parent star there, the star that disappeared. So, and then this is the pulse of neutrinos. We see that, well, they had more or less energies around 30 mega electron volt. This is the energy to which this nascent neutron star is heated, right? If we convert it into Kelvin, it would be some billions of Kelvin. So the body, the neutron star at birth is very hot. And all the energy, so it starts, this neutron star that is born it starts to cool through neutrino emission because now no other particles goes away. Yeah, all the other particles are trapped inside this very dense configuration. So neutrinos are gradually cooling the neutron star to lower energies. You see that the energy is decreasing with time. Then the pulse lasted some 10 seconds. That's consistent with the time of diffusion of neutrinos out of the neutron star. So more or less this observation confirms this idea that I was propagating to you moments ago. Yeah. We are of course waiting for the next supernova explosion. Actually, this super Kamiokande is already the advanced version of Kamiokande. Well, the detector that detected the neutrino pulse from supernova, it was called Kamiokande. Now the detector is larger, it's called super Kamiokande. And when you will be grown up, the next version will be called, try to guess, hyper Kamiokande, right? For your kids, I don't know what is the next superlative term. So, well, yeah. So now there are neutrino detectors running 24 hours, 7 days, waiting for the next supernova, which we suspect is already underway. You will see in exercises. Yeah. Good. So this was about the neutron star in general. Let's try to look at some other, well, properties of neutron star that make it pulsar. By the way, this supernova 87A, the progenitor star of this supernova 87A is good for doing neutron star. I forgot to tell that this possibility that neutron star is left over from supernova explosion. By the way, I didn't tell about supernova explosion yet. I only told about collapse, right? So everything goes on its own, yeah? Then imagine if the star is, I don't know, 10 solar masses or larger. All these rests of the star, when the nucleus is gone, it starts to collapse onto the star, right? So the mass of the neutron star starts to grow. And by default, we should be left with no neutron stars at all, because for neutron star, the maximal mass is about, I don't know, 3-4 solar masses. So if the matter of around the neutron star is not ejected into space, the neutron star will collapse on its own turn, in its own term, to produce a black hole. Sometimes this is what happens, right? So we expect that some fraction of this collapsing stars results in leaves a remnant that is neutron star, some fraction of them leaves a remnant that is black hole, right? But we know that neutron stars exist. This means that matter was ejected from the vicinity of the neutron star. And we even suspect how it happened. Remember, well, if I come back to this story that neutrinos have to diffuse away from the neutron star. When doing this, by the way, when the neutrinos scatter, they leave a bit of momentum in the neutron star itself. Then they escape from the neutron star and they have to cross the body of the star, yeah? They cross it more or less without interacting, but a good fraction of neutrinos, maybe 1% of them, interacts at least once inside the envelope of the star, yeah? This process gives momentum, mechanical momentum to the envelope. And it is this mechanical momentum that ejects matter. So in fact, the pulse of neutrinos is an important ingredient of a mechanism of an explosion. It converts gravitational energy of gravitational collapse, of shrinking, into the energy of explosion, right? Of ejecting matter. This gives, well, we think that this gives the mechanism for supernova. The whole idea is called neutrino-driven supernova explosions. It's a sophisticated subject of astrophysics on its own. People are running supercomputer simulations to demonstrate that this works with variable success. So it's some work in progress. Okay, so now still if we are in this lucky situation that neutron star survives after supernova explosion, not much matter has fallen onto its surface, so it is preserved. So what are the properties of this neutron star? One thing to notice is that it will be very fast rotating. What is the argument here? When we have a collapse, it goes with the conservation of angular momentum, because the core of the star, the iron core is isolated system. It doesn't have contact with anything and doesn't have means to dissipate angular momentum. If I write the expression for the angular momentum, so it's m times velocity, which is omega r, times the size. So this combination is preserved. Angular velocity is 2 pi over the period. So I can tell that if this is constant, the period goes as the size square. That's a simple calculation, right? Now let's do a small imaginary thought experiment, right? Let's take our sun and try to shrink it to the size of the neutron star. What is our expectation in this case? So the sun is a star of the size 10 to 11 centimeters. It rotates with the period 27 days, I think. If I use this relation, shrinking the sun from 10 to 11 centimeters to 10 kilometers, this is the size of the neutron star, gives me a change of 5 orders of magnitude. Then squared, this tells me that, well, I divide 27 days by 10 to the 10, it brings me down to millisecond period. So this is an impressive machine, right? There is a lot of rotation energy stored in this system. Yeah, I shrink the sun to the size of Lausanne and make it rotate with kilohertz frequency, right? So with millisecond period. Another fact of the same nature, well, ideologically, is that, well, all the stars are magnetized. In the sun, we have a dipole magnetic field that is more or less 1 Gauss. We have stronger disordered magnetic field, which can be kilogauss. And the sun is a conducting media, right? So if it shrinks, the magnetic flux is conserved. If I write the expression for magnetic flux, this is strength of the magnetic field times the area, surface of the star. This is conserved. Again, let's do the same thought experiment. I shrink the sun by 5 orders of magnitude. The magnetic field would grow by 10 orders of magnitude. So my magnetic field of 1 Gauss in the sun would become 10 to the 10 Gauss. So we start to get a feeling that there is something interesting to, well, there should be some phenomenon related to a compact star rotating with kilohertz frequency and strongly magnetized. Let's try to see what is the observational signature of this machine. Yeah, my next topic in the next 10 minutes will be to explain what is pulsar. So this machine works as a powerful particle accelerator, ejecting high energy particles in some beams. Yeah. And that's why the whole machine works as pulsars, because high energy particles ejected into some direction, they would lose energy in radiative ways, they would produce photons, right? So there are beams of radiation shooting from the neutron star, and the whole thing is rotating, right? So sometimes if we observe from the side, this beam would point to us, sometimes not, away from us, right? So the whole thing is pulsating, right? Because it's rotating. So how does it work? Particle acceleration next to the neutron star. You still follow me? Yeah, so it's again a change of topic, right? So my idea is that this magnetized rotator works as a powerful electric generator. it would generate high voltage. Don't look at the bottom of the slide because the answer is there. I want to impress you. I should have divided the slide into two. So how this generator works? Let's look at the surface of the neutron star. So inside, it's mostly neutrons, neutral particles. They don't support current and so on. So, but the surface, the crust of the neutron star still has some protons and electrons. And these protons and electrons, they are rotating together with the star. Now, there is magnetic field. If we think about magnetic dipole, let's think about the star as a solenoid, right? Perhaps there are currents circulating around the equator, and inside the solenoid, magnetic field is like this. Outside, it will be dipole. And let's look at, for example, an electron or a proton that is moving somewhere close to the surface. So it will be subject to Lorentz force, right? It has velocity. If I take an electron somewhere here, it has velocity toward us, magnetic field over there, right? So the Lorentz force will be pointing inwards, like horizontally inwards here for electron at the edge here, right? Then what does it mean? There is a component of the force that will try to squeeze electron into the interior, but it doesn't want because all the places are taken in, well, so it doesn't want to sink into interior. But there is a component of the force that is tangent to the surface. There is no resistance here. Electron would follow this force and be displaced gradually toward the pole because of this component of the Lorentz force, right? Yes. It's a bit of, well, this left, so the rule of left or right hand depends. So the direction is like this. Now, if I take proton, it's the particle with opposite charge. So if for electron, the force was pointing inwards, for proton, the Lorentz force, this V cross B, will point exactly in the opposite direction, outwards, yeah? So the tangent to the surface component of the force will be the opposite. So if electron is pushed to the pole, proton will be pushed to the equator. And after a while, even if I start with mix of protons and electrons, the rotation and magnetic field would make charge separation. All the electrons will go to the poles and all protons will form a band on the equator. This means that I would have generated electrostatic field, right? Because, well, here is my sketch of the line of the field. The field lines would always go from positive charge to the negative charge. They would go outside the neutron star, but also along the surface of the neutron star, there will be electric field. I can even predict what is the strength of the field. My charge separation result would produce electric field, which would actually ultimately resist the Lorentz force, right? It would be in the opposite direction. So the Lorentz force was pushing electrons to the pole, but now the pole is crowded with electrons. So the electrostatic field is pointing away from electrons. It's repelling electrons, right? And ultimately, I would reach a situation when the net force working on particles is zero. So the electric field, the back reaction electric field, would exactly compensate the initial Lorentz force. That's a reasonable situation. At this moment, charge separation will just stop because there is nothing that pushing electrons to the poles and electrons and protons to the equator. Yeah. I make a small estimate. This is my estimate of the strength of electric field. I know that this is an electrostatic field, right? So the electric field is the gradient of the potential, electrostatic potential. And for the electrostatic potential, I will do order of magnitude like this. Omega is 2 pi over T. R is the size of the neutron star. B is the strength of magnetic field. So the order of magnitude for potential is like this. I find some impressive number, 10 to 20 volts. If I have a neutron star with magnetic field 10 to the 12 Gauss, this is typical. We will not see it today, but maybe well, we know our ways to measure magnetic fields around neutron stars. The size is 10 kilometers. That's what we estimated. And I take, of course, the shortest period that we saw before, right? Millisecond. So this is well beyond the whatever electric generators here on Earth, right? Have you ever seen electric generators somewhere? We have some accelerator here in the building, right? You have labs. So who is particle physicist around that? Yeah. So did you see accelerators or Van der Graaf generator here in the building? What kind of accelerators do you use? You do. Well, if I don't know where it is possible here, if you go to Paris, go to Palais de Découverte, next to the Champs-Élysées. For kids, they do experiments like this. They put some Van der Graaf generator that generates some tens of thousands of volts. They connect kids to these generators and they make them shoot into each other with lightning and so on. That's an impressive machine. But these generators are tens of thousands of volts, right? This is 10 to the 20 volts. So if we put a proton into, so if we drop a proton somewhere next to the neutron star, if we imagine that it would cross this potential difference, after all, it will have energy 10 to the 20 electron volt, right? Because the charge of the proton is the same as electron, right? A particle going through the potential difference would go, the energy would take the energy that is potential difference times the charge, right? So if you remember, I was mentioning cosmic rays at the first lecture. 10 to the 20 electron volt is the energy of the highest particle that we have ever seen in cosmic rays. It was this tennis ball exercise, right? That was the energy 10 to the 20 electron volt. So this is a very powerful electric generator machine. I don't know, for whatever reason, the mechanism is called unipolar inductor. It's a name. So what do? I have a couple of minutes. Maybe I finish in a couple of minutes the story of this generator. So if we do a powerful electrostatic field generator here in laboratory, we would always face a problem like this. We would have an effect of discharge of if we have, we can do a simpler thing, right? If we do a capacitor, we connect the capacitor to a battery. Like this. So if we increase the voltage, sooner or later there will be a discharge that will try to push electrons through the capacitor, right? Why is this? It is because of effect like this. Nothing is empty around us. There is some medium inside the capacitor, some residual air or something, yeah? So imagine that, this medium will be always a little bit ionized because nothing is neutral in nature. So if there is a wild electron somewhere here, and what is this? This is wild electron. I better put minus. So there is a wild electron somewhere here. It will be accelerated. It will try to get the energy that is E times V. But before reaching the cathode, cathode or not, where it goes to cathode, it will perhaps bump into an atom. Doing this, it will perhaps ionize it, liberate another electron. This electron will be again accelerated. It will bump into an atom. It will ionize it, and so there will be avalanche of particles, right? Which would sort of bring a lot of electrons here and maybe a lot of ions to the other side. And this will be a back reaction that will discharge the battery, right? That's our everyday experience. Sometimes it goes in spectacular way with the lightning and so on. The capacitor can burn and so on. Yeah, and that's we convert electric field energy into burning or lightning energy. The same thing happens there in next to the neutron star. So my first model of the neutron star was a neutron star in vacuum, but of course nothing is in vacuum. Yeah, even in space there are some particles flying around. Now imagine that I drop an electron or a proton somewhere in the middle of nowhere. The electron gets accelerated, and well, nothing is straight also around neutron star, right? So when it is accelerated, its trajectory will be curved. Means that well, anyway, a particle that is accelerated starts to emit radiation. Photons emitted by accelerated electrons, they are gamma rays. They have large energy. The energy that is sufficient to produce electron-positron pairs if they bump into, for example, another photon, or they can also spontaneously create pairs when they go in magnetic field. So there will be electron-positron pair production taking place around the neutron star. Then, as in the capacitor here, next generation of electrons and positrons will be accelerated, will produce photons that will bump into another, well, in whatever particles produce more electron-positron pairs and so on. So the same avalanche effect will be present around the neutron star. So at the end, all the space around the neutron star will be full of electron-positron plasma. This electron-positron plasma is called pulsar magnetosphere. So now the system complicates, right? So we started from a neutron star that is fast rotator with magnetic field. This fast rotator works as electric generator. Electric generator discharge tends to dress the neutron star into a coat of electron-positron plasma. Now all this star with the coat of electron-positron plasma rotates very fast, right? So these particles in electron-positron plasma, they are swept by, they are co-rotating with the star, right? And after all, this fast rotation leads to the effect that, well, there is centrifugal force. There is some effect more complicated than this. But this electron-positron plasma is ultimately lost into space. It is constantly lost into space and refilled by this particle acceleration and pair production effect. This leads to overall appearance of the pulsar. So there is, in this Crab nebula, there is a neutron star in the center. I would not be able to localize it like this. This is a composite image made of radio in red, X-ray in blue, visible in this filamentary structure. So somewhere inside there is a neutron star that is dressed in this electron-positron plasma that is lost into space. These high energy electrons and positrons, when they go, on occasion, they bump into the rests of the exploded star. And they start to lose energy by producing synchrotron radiation and, well, in radiative way. This causes a glow, a nebula-like glow around a fast rotating neutron star. The whole phenomenon is called pulsar wind nebula. Okay. So that's quite the road that we made today. We started from a death of massive star, right? That has such unforeseen consequences. It starts to, well, the remnant of the star starts to operate particle accelerator. And of course, these pulsars, these are the sources that are dominating this very first map that I was showing here in the first slide. Yeah. So this Crab pulsar, inside Vela supernova remnant, there is a pulsar. There is a couple of other bright pulsars nearby. So all the brightest sources along the galactic plane, these are this pulsar wind nebula. And also, if we look in GeV band from Crab pulsar, we really see that it is pulsating regularly we know that it's pulsating with 33 millisecond period. Yeah. So nice objects to study for astronomers. Good. So I'm done for today. We make a break till, or either a questions. It was a story, right? So follow the story. Was everything clear? Good. So we make a break till 10:20, and then it's Volodymyr who